Something hit Earth today. Not a big one, a small rock, maybe a meter across. It vaporized in the upper atmosphere at 50,000 miles per hour. Most people didn't notice. A few satellites caught a flash. It happens more than you think, more than almost anyone knows. In the last 30 years, objects large enough to level a city block have entered Earth's atmosphere hundreds of times. Most burned up, most hit ocean, most were detected only after the fact, or not at all. There's a rock floating through the inner solar system right now that will one day hit us. We don't know if it's 50 meters wide or 10 kilometers. We don't know if it will arrive in our lifetime or in 10 million years. But astronomers know with near certainty that it exists. The question isn't whether Earth gets hit again. The question is, will we be ready when it does? And the answer, for the first time in the 4 billion year history of life on this planet, might actually be yes. To understand where we're going, you have to understand what's already happened. 2 billion years ago, a rock roughly 15 kilometers wide struck what is now Sudbury, Ontario, in Canada. The energy released was equivalent to tens of billions of nuclear warheads going off simultaneously. The impact structure it left behind is still 130 kilometers across. The rock that made it is long gone, vaporized on contact. In South Africa, a crater from a similar era stretches nearly 300 kilometers. It is the largest confirmed impact scar on Earth's surface. When it was made, complex life had barely begun. Then came the one that changed everything. 66 million years ago, a 10-kilometer asteroid hit what is now Mexico's Yucatan Peninsula. In the following months, it killed 3 out of every 4 species alive on Earth. Not by the initial blast, though that alone was incomprehensible, but by what came after. Debris launched into orbit re-entered the atmosphere, made heating the sky to oven temperatures. Wildfires swept every continent simultaneously. Then dust and soot blocked the sun for years. The food chain didn't collapse. It was incinerated. The dinosaurs had been on Earth for 165 million years before that rock arrived. They didn't see it coming. They had no way to. We do, which is exactly why this story doesn't end there. February 15th, 2013, Chelyabinsk, Russia, 9:22 in the morning. A meteor entered the atmosphere traveling at 42,000 miles per hour. Yeah, it was 20 meters across, smaller than most people's houses. It never even reached the ground. 30 kilometers above the surface, the pressure became too much. It exploded. The shockwave shattered windows across 6 cities. Glass flew inward through schools, offices, apartment buildings. 1,600 people were injured in a single morning. Thousands of buildings were damaged. The explosion released energy roughly 30 times more powerful than the atomic bomb dropped on Hiroshima. Nobody saw it coming. Not because we weren't looking, because it came from the direction of the sun. A blind spot in every ground-based telescope on the planet. A 20-meter rock, 0 warning, 1,600 injuries in one of the most densely populated regions of Russia. Now consider this, the asteroid that killed the dinosaurs was 500 times larger, and it released energy not 30 times greater than Hiroshima, but billions of times greater. Most people think an asteroid impact is like a big meteor strike. Rock hits ground, big explosion done. It doesn't work that way, not at that scale. When a 10-kilometer object traveling at 20 kilometers per second enters the atmosphere, the air in front of it cannot get out of the way fast enough. It compresses, it superheats. The fireball it creates is visible from 1,000 miles away, brighter than the sun. On impact, the asteroid doesn't dig a hole. It behaves like a fluid. The kinetic energy, accumulated over millions of miles of travel through the vacuum of space, releases in seconds. The rock vaporizes. The surrounding crust vaporizes. A crater 150 kilometers wide forms in minutes. The shock wave travels through the ground faster than sound travels through the air. But here's the part the movies always skip. The ejecta, billions of tons of rock and dust, gets hurled into the upper atmosphere and into low orbit. As it falls back down, friction heats it. The sky turns red globally. Surface temperatures spike above 200 degrees Celsius for hours. Not near the impact site, everywhere. Then the smoke from a million simultaneous wildfires rises into the stratosphere. It stays there for years. Sunlight stops reaching the surface. Temperatures crash. Plants stop growing. The creatures that survive the initial heat die in the cold and the dark that follows. One rock, one afternoon, the end of an era. And the terrifying part? That is not even the biggest impact in Earth's history. The good news is that we are looking. Dedicated sky survey programs photograph the same sections of the night sky night after night. Stars stay fixed. Asteroids move. Automated software compares images, flags, anything that drifted. And within hours, a new object enters the database. From that initial detection, astronomers calculate a preliminary orbit. And this is where things get interesting, and where the media often loses the plot. Your early orbital calculations are uncertain. There's a margin of error in the telescope measurements, a margin in the distance estimate, a margin in the speed. Put all those uncertainties together, and you sometimes get a non-zero probability of Earth impact, sometimes a significant one. And so the headlines come, new asteroid could hit Earth, and technically they're not wrong. But here is what actually happens in almost every single case. More observations come in over the following days and weeks. The uncertainty shrinks. The orbital path resolves, and the probability of impact drops to zero. It has happened dozens of times. The rock that was 1 in 10 becomes 1 in 10,000, becomes zero within a month. As of now, scientists have cataloged approximately 99% of all near-Earth asteroids larger than 1 kilometer, the kind capable of causing global catastrophe. It's none of the known ones are on a collision course with Earth in the next century. Sit with that for a second. That is genuinely extraordinary news, but 99% is not 100%. And the problem gets worse the smaller you go for objects in the 100 to 500 meter range, large enough to destroy a major city or an entire small country, but not large enough to threaten civilization. We found perhaps 40% of what's out there. For objects under 100 meters, it's far less. There's also the blind spot that caught Chelyabinsk, the sun. Any asteroid approaching from roughly the same direction as the sun is invisible to ground-based optical telescopes. It's not a small region of sky. It's a significant one. Space-based infrared telescopes can partially compensate. Infrared light passes through daylight. But dedicated coverage of that zone is still limited. Hundreds of small to medium objects have entered Earth's atmosphere in recent decades. Most people on this planet have no idea. The ones that didn't burn up fully hit ocean or remote terrain or were simply too small to cause damage. But small enough to do no damage is a category that keeps shrinking the more closely we look. In September 2022, NASA flew a spacecraft into an asteroid on purpose. The mission was called DART, the Double Asteroid Redirection Test. The target was a 160-meter moonlet called Dimorphos, orbiting a larger asteroid called Didymos. Neither was threatening Earth. This was a test. The spacecraft weighed about 570 kilograms. It hit Dimorphos at roughly 14,000 miles per hour. The collision released a plume of debris that extended thousands of kilometers into space. Then scientists watched. Before impact, Dimorphos took 11 hours and 55 minutes to orbit Didymos. After impact, it took 11 hours and 22 minutes. DART had shortened the orbital period by 33 minutes, 4 times more than the minimum threshold for mission success. For the first time in the history of our species, we had deliberately moved a celestial body. But here's the honest limitation. DART worked because we had a small target. Years of preparation and a spacecraft the size of a vending machine was sufficient for the job. Against a 10-kilometer impactor, the kinetic approach may not scale, which is why scientists are already developing the next generation of methods, gravity tractors that slowly nudge asteroids over decades, nuclear standoff detonations that heat one face of a rock and use the escaping gas as thrust. None of them have been tested, but the physics is sound. The most critical variable always is time. Given decades of warning, you don't need much force. Given months, your options collapse rapidly. This is exactly why early detection isn't just interesting. It is, in the most literal sense, the difference between survival and extinction. In the mountains of northern Chile, the Vera Rubin Observatory is coming online. Its camera is the largest digital imaging system ever built for astronomy, 3.2 gigapixels. Its primary mirror is 8.4 meters across, and its core mission is to photograph the entire visible night sky every few days, continuously for a decade. To understand why this matters, previous sky surveys could cover large sections of the sky on timescales of weeks. Vera Rubin does the entire visible sky in roughly 3 nights. Then again. The catalog of known near-Earth objects is about to explode. Scientists expect Vera Rubin to detect hundreds of thousands of previously unknown asteroids in its first years of full operation. A significant portion will be in the size range we currently know the least about, the 100 to 500 meter objects, the city killers. More detections means more orbital calculations. More orbital calculations means fewer surprises. And fewer surprises, in this particular context, means fewer civilizations that never saw it coming. Here is the honest summary of where we stand. The threat is real. The physics is unambiguous. Objects capable of ending human civilization exist, and they cross Earth's orbit. The question of whether one will eventually reach us is not a matter of if, it's a matter of when. But we are not the dinosaurs. We can see into the dark. We've already changed the orbit of a space rock. We're building machines that will scan the entire sky every 3 days. We know what to look for. We know how to track it. And for the first time in history, we're developing the tools to actually do something about it. The most dangerous asteroids, the civilization enders, are mostly found. None are coming soon. The medium ones, the city killers, are where our attention needs to go next. And there, we are very much still in the early innings. The universe doesn't care about us. It never has, but for the first time in 4 billion years of life on this planet, one species looked up at the sky, understood what was coming, and decided to do something about it. Yeah, that is not a small thing. If you want to track real near-Earth objects, asteroids that are actually being monitored right now, NASA's Center for Near-Earth Object Studies publishes a live risk table. It's public, it's updated daily, and I guarantee reading it will change how you look at the sky. If this video made you think differently about what's above us, share it with someone. Most people don't know about Chelyabinsk. Most people don't know about DART. Most people have no idea how close we've already come and how close we're getting to actually being prepared. That changes one conversation at a time.